Okay, I want to point out that there's a negative sign that we have to keep track of. In the last lecture, you may have forgotten by now, but there was a sign issue with the derivation when we're working with the potential from the electric field. So let me illustrate this to you, what I'm trying to say. So a quick recap from the February 10 lecture is that the electric field is written as the gradient, the negative gradient of the potential, and that is equation 2.23. And the other thing we know is that the curl of the electric field is zero, and that is equation 1.45 and homework 1. Then the next thing that we have talked about is that the potential difference between points A and B, right? So potential difference between any points A and B is now it's just the reverse of this relation, right? And so it's a negative E dot dl from points A to B. And if you're defining the potential at some point R, then you just take the point A to be infinity, usually. In very rare cases, if the charge distribution extends out to infinity, then maybe this doesn't, then you can't do this. But generally, you set the 0 point at infinity. So A is infinity and B is the point R. And so this becomes E dot dl. Now, what I want to start with is that, there are some negative signs that you have to keep track of when you apply this formula. Okay, so I'm going to apply this to the most basic case, okay, and I want you to pay attention to how the negative sign works out, because I remember I stumbled in class with this and I'd said I'll talk about this later. So I'm doing that now. Okay, so if you have a situation where you have your, let's say a point charge, the simplest case, okay? And it's the simplest case because I know that the electric field at position R, let's say, so let me just indicate that. Let's say that um, we're here. Okay, so this would be vector R. And let's say, the electric field at this position we know is just Q divided by 4 pi epsilon naught magnitude R squared, and it points in the unit vector R, right? And so the unit vector R, of course, points in this direction along this red arrow. We also know that the potential at this point is Q divided by 4 pi epsilon naught R, but I want to derive it. Okay, and that'll help us keep track of what's happening with the negative signs. The reason this is a subtle point is that the dl is coming in from infinity out to this point R. Okay, so so dl and dr are oppositely directed. Okay, because if I and we discussed already that all that really matters for this radial field, is just the radial path. So let's say I'm coming in from infinity toward, right? If I want to prove this formula, and I want to go over that because there's a confusion with negative sign which students often have. So let's say I'm coming in from infinity toward this point R, right? That's what this integral says. So if I'm coming in from infinity toward this point, then you notice how dl is pointing this way. On the other hand, a dr on r is going to point in this direction. And this is what leads to some confusion. So I'm going to talk about this right now. All right, so it's just a simple point, but a subtle one that I would like to make. So let me start with this definition. Okay, so I'm going to use this definition to derive um, the expression for V sub r, this guy. All right. Okay, so let's start. So what do I have? I have that the potential at this point R, okay, is equal to negative the electric field dot dl as I come in from infinity to the point R. So I'm coming in from infinity to this point R, okay? Now, the first thing I notice is that the E, the electric field, is pointing out radially, and the dl is pointing in. So the dot product here, right, is going to be, so E dot dl, right? The E sub r points outward, and so that's your, right? So the vector E field, E, is vector E sub r, right? That's what this guy is. Okay, so I got that. That's what vector E is. And then this is dot with dl, which is a negative dr, right? So that's what I need to calculate. And then, of course, the dr, the vector dr, and the vector E sub r are pointing in the same direction. So this is equal to minus, you see now the vectors are gone. It's a cosine of 0. And so I have this, okay? But so that's one place where, because of the dot product and because of dl being equal to negative dr, right? I've used that here. dl is equal to negative dr. Okay, that's what I used here. So that's good. But now you see my limits of integration have, here I was integrating dl, which was going from infinity to r, but now it has become an integral over, so this is going to become an integral over, so there's a negative here, and there's a negative here, and it's an integral over dr now, you see? So L, the variable dl was going from infinity to r, but because dl and dr have opposite signs, dr, the integral will go from r to infinity. You see, that's an important point. So I want to say here that when when integration variable dl changes to dr, then the limits of integration change too. Okay, so for dl, we were going from infinity to r. Well, for dr, we will go from r to infinity because they're pointing in opposite signs. So you see, I got this. Okay, and so this now becomes integral r to infinity er dr, right? And now if you perform the integral, you will find that you will get this answer because this would be, well, what is E sub r? q divided by 4 pi epsilon naught is constant. Then I have integral from r to infinity, and I have a 1 over r squared for the e sub r, right? So that's the magnitude of e sub r right there. And then I still have a dr. So this is, now you can see the 1 over r squared will give you a minus 1 over r, right? And this is from infinity to r. And so the 1 over infinity gives you a 0, and then you have a minus of 1 over r, right? When you take the limits. And so you will get q over 4 pi epsilon naught r. And that is the answer, right? You don't have any negative signs spoiling this. Okay, so just bear in mind that, there was this place where the negative sign had to be taken into account, and then right here also you have to be careful with changing the limits of integration, right? You see how we changed it from infinity to r to infinity. Okay, so there you go. We have these two places where the negative sign mattered. Okay, all right, I'm going to stop this recording now that I've made my point.